Hello all. In this video, we're going to be covering section 13.2. So this is kind of like calculus for vector valued functions. And by calculus, we usually mean derivatives and integrals, right? All based on this idea of the limit. So in 13.1, we learned how to do limits for vector valued functions, which were really straightforward. We just took the limit inside the vector. And now we're going to use that idea of the limit to figure out how to deal with derivatives and integrals for these vector valued functions. So once again, we're going to be working with these vector valued functions. So like a vector valued function might be, we might denote it with this letter S from R to Rn, okay? I'm using the book, I think, uses lowercase r, but I switched to S just because there's a lot of R's in this. I don't want to say R from R to R, and that just sounds confusing. Okay. So remember that a lot of what we're doing can be generalized to just generally n dimensions. In particular, though, we're going to be interested in 3 dimensions. So we're going to start with defining the derivative for vector valued functions. But before we do that, let's recall the definition for the derivative of a function of a single variable. Okay. So think about your functions that you've seen in Calc 1 and 2. These normal, I shouldn't call them normal because there's nothing particularly normal about them, but these functions we're used to. So f from R to R. Okay. Remember the function, or excuse me, remember the definition of the derivative. So we have a couple pieces of notation here. So df dx. Okay, so remember this means like we're differentiating f with respect to x. And a lot of times that's just denoted, the derivative of f is just denoted f prime. Okay, and if we're talking about the derivative at a specific point x sub 0, maybe we say f prime of x sub 0. Okay. So remember what this is. Okay, the derivative of f at that point x0, well, that's a limit. And if the limit exists, it's going to be equal to this thing. Okay. So this is the definition of the derivative in its kind of limit form. We have the f prime x0 is equal to this limit as x approaches x0. Fx minus fx sub 0 over x minus x sub 0. And another way you might have seen it, and this is the kind of notation that the book uses and that I'll use for the rest of this section. You might have seen this. These two things are completely equivalent. Okay, so we might have just phrased the limit a little bit differently. Okay, so the derivative at x0 is equal to the limit of f of x0 plus h minus f of x0 over h. Okay. And remember the kind of the caveat or the little stipulation we have here, that this definition only holds, these definitions only hold if this limit exists, right? If these limits exist. There's nothing to guarantee that this limit is going to exist, but when it does, okay, that's going to give us the derivative. Now remember our kind of geometric intuition behind derivative. So let's say this is my point. Oops. Let's say my point x0 is here. And this curve is my function f of x, the graph of my function f of x. What is the derivative? And what is this fraction in particular? So before we even talk about the derivative, what is this fraction? I could think of this fraction as rise over run, essentially, right? These, if I kind of think about what this is, let's say h, x is xo plus h, or xo minus a, let's say h is negative. Okay, so this would be xo plus h, right? Well, what is this quantity here? That'd be this y coordinate minus that y coordinate. And then I'm dividing by that distance. So that's like the slope, right? That gives me the slope of the line between these 2 points. Okay. And really the derivative is considering a lot of these lines, a lot of these slopes. And we're taking the limit as that distance between our points gets smaller and smaller and smaller. And that gives us, that limit will give us the slope of the line, of the tangent line, okay? The line tangent to our curve at that point, x0, okay? So if our function is differentiable, there's only going to be one tangent line, right? And the derivative is going to be the slope of that tangent line. Okay. Now let's switch our thinking to vector valued functions. Okay. It turns out we can define the derivative of vector valued functions in the exact same way. So let's consider our vector valued function s from R to Rn. Okay. So we're just going to define this derivative, this s prime of t. Okay, so again, we have this couple pieces of notation here. We have ds dt. Okay, so that's just the derivative of s with respect to t, and that might be denoted s prime of t, or if we're talking about a specific point, maybe I'll write t sub 0. Okay. Well, that's just going to be this limit here. We're gonna try and find this limit. If that limit exists, we call it the derivative. So this fraction is set up the exact same way as in our single variable case. Okay, but maybe we have a little bit different interpretation of it. Okay, we just need to look at the kind of inputs and outputs. Okay, so when I had f from R to R, right, I was working with this fraction here. And I was taking that limit, right? And what were each of these components? Well, that was just a number, right? It's the value, the function value of x plus h. And this is just a number. It's just a function of the function value at x. And then this is a number, right? That's the number h. Now, in my vector value case, well, these things on top are vectors, right? I have the vector, my vector valued function at t plus h, minus my vector valued function at t, and then I'm dividing by a number, a scalar. So a little bit different. But, you know, does this thing make sense? Yeah. Think about it like this, like pull the h out front, okay? Now this is just a number, right? Okay, this is just 1 over h, that's still just a number. And what's going on in parentheses? We have one vector minus another. Well, we can do that, right? So this is just a vector. And then I'm multiplying and then by this. What is this? This is a scalar. So really what I have is just this fraction is just a vector times a scalar, and there's nothing wrong with that, right? So maybe it helps to think about it in this format. So but this also gives us the intuition that, okay, in my single variable case, my derivative was just a single number, right? You know, maybe this gave me my slope at the point xo, the slope of my tangent line, but that derivative is still just a number, okay? Maybe that number represents the slope, but it's just a number. But in this case, in my vector valued function case, my derivative is going to be a vector, right? It's going to end up being, I have a scalar times a vector, and I'm taking a limit. That's still going to give me a vector. Okay. So this derivative, s prime of t, is a vector. Okay. So how can we think about that? So let's say this is some curve. Let's say this is the graph of my vector valued function. Let's say this is the graph of S of t. What is S prime of t? Okay. Well, this vector valued function, it still has tangents, right? But now the tangents are in 3D. Okay. Okay, so if I wanted to consider a tangent line at that point, maybe it looks like this. And well, it turns out that S prime of t is still sort of like a slope. The problem is that since this curve is in 3D, right? It's in 3 dimensions. A single number can't really tell us the slope of a tangent line, right? Like if I told you the slope of the tangent line is 4, okay, what does that mean in 3 dimensions? Like, is it going 4 units this way? Is it going 4 units that way? What's going on? So to really accurately describe a tangent line, we don't need we need more than just a single number. We need a vector. Okay. So when I find S prime of t, okay, that's going to be the tangent vector. Okay. So maybe I find S prime of t and it gives me a vector, and that vector has coordinates. Let's say it's pointing back in this direction. Maybe it has coordinates 1. How about -1, 1, 1. Okay. What does this mean? It means at this point, if I drew a tangent line to this curve at that point, this tangent line is parallel to this vector. Remember how we wrote equations for lines in R3? So this is going back to what, 12.5 maybe? To write the equation of a line in R3, what did we need? We said RT was equal to like R0 plus TV, where this is a scalar, and then this is a vector parallel to our line. Okay. That and that was kind of analogous to y equals, b plus mx, sort of, where m is a slope. Okay. Really, let's write it like x times m. Okay. Where this was a slope. Now in R3, this vector is kind of playing the role of our slope. Okay. So what I'm saying is, when we have this curve S of t and we calculate S prime of t, that is going to be, it's going to be a vector, and that vector is parallel to the tangent line. Another way of phrasing this is S prime of t will be a vector that points in the direction of the tangent line. It kind of gives us our slope in all directions, like our 3 kind of cardinal directions, x, y, and z. So going back up to here, let's say this curve is my S of t. I find my S prime of t. That gives me a vector, and we said it was -1, 1, and 1 in this case, right? So maybe at this point, my vector, my tangent is -1, 1, 1. that means my tangent line points in this direction of -1, 1, 1. Okay, so this is my vector, and I know my tangent line points along this direction. So we could still think of the tangent vector as a sort of slope, but in higher dimensions. So again, the terminology we're using here, when we have this vector valued function and we calculate its derivative, s prime, that vector is going to be the tangent vector. And again, they have the similar idea of direction, right? When I'm talking about a curve, the graph of my function f r to, from r to r, just my function of a single variable, right? And I'm talking about the slope, right? That's basically the direction of my tangent, right? It's just that there's really, you know, there's not much information to say here. This orientation of my tangent vector can be completely captured by one number, the slope, right? So there's no kind of complex three-dimensional orientation. It's just how steep my vector is. Okay, that's kind of how we can interpret slope. For these vector valued functions, you know, we need a bit more information than just a single number. Okay. We need kind of how my curve is oriented, how my vector is oriented. So we need more than just a single number. All right, so now that I've rambled on and tried to give you an intuitive idea of what this derivative is, let's talk about how to calculate the derivative. Now remember from when we reviewed the definition of the derivative for a single variable function, that really this derivative is just a limit, right? It's the limit of that fraction we're looking at. And we can define the, and we actually did already define, right? We defined the derivative of this vector valued function as a limit, right? Now remember from 13.1 that we can take limits inside our vector. So let's say I have a vector valued function RT and I'm trying to calculate the derivative. Okay. Well, this notation here is just for limit. So if I'm trying to find the limit of this function R of t, I just take the limit inside the vector, right? So if R of t is made up, it's got components f of t, g of t, h of t. When I take the limit of the vector valued function, I just take the limit inside the vector. So I take the limit of f, I take the limit of g, I take the limit of h. In other words, we can take the limit inside the vector. And the derivative is going to function the exact same way. So let's say we have a vector valued function s of t. And again, it's got components f, g, and h. Okay. So let's consider the derivative of s of t. Okay. We know from our definition, our previous definition, it's going to be this, this limit, right? And I'm going to use k here just to avoid any confusion with notation. Okay. It's still the same form of the limit. So we have this fraction here. We have s of t plus k minus s of t divided by k. So remember, this is a vector minus a vector, and then I'm dividing by a scalar. Well, forget about the limit for a second, and let's just consider that fraction, and let's kind of write it in component form, okay? Well, I can rewrite this fraction like this: f of t plus k, g of t plus k, h of t plus k, minus f of t, g of t, h of t, all divided by k. And let's bring this k out front. Okay, so let's bring this k out front. All right. And I have this. Now I have one vector minus another up here. Well, I can write that as a single vector, right? By putting it all together in one one set of brackets. So I have f of t plus k minus f of this should be f of t, and then g of t plus k minus g of t, h of t plus k minus h of t, and then I'm dividing by k out here. I can think of that as scalar multiplication. Well, remember with scalar multiplication, if I have a times a vector, that's I know my vector is, say my vector is 1, 2, 1. Okay, a times that vector is the same as a times 1 plus 2 times, or a times 2, a times 1. Okay, so I can bring this constant inside my vector and multiply it by the components. So let's do that with our k. Okay, so I'm taking this k and I'm bringing it inside and multiplying it by all my components. So now I end up with this vector. Okay, and I have a limit out front. So now I'm pretty much as simple as I can be with this fraction. But now what I'm going to do, remember when we have a limit of a vector valued function, we can take the limit inside the vector. So I'm going to take the limit inside and look at the limit of each component. Well, look at this first component. What's going on here? F is just a function from R to R, right? So this is just our normal calc 1 and 2 idea of a function. And what is this limit of that function? Well, that's just our definition for f prime, right? So this first component just becomes f prime of t. Same thing with the second and third components. This is the definition of g prime. This is the definition of h prime. Okay. So I take the limit inside my vector and I just end up with the derivatives of the components. Now, if that explanation, is a little bit, I don't know, esoteric for you, a little too abstract, just think of it like this. If I have a vector valued function and I want to take its derivative, I just take the derivative of the components. Okay. Now this means we need to know all our derivative rules from Calc 1 and 2, but other than that, there's not, we don't really need too much knowledge. We just have to know that we can take the derivative inside the vector. So let's say this is my vector valued function r of t. Let's calculate r prime of t by just taking the derivative inside the vector. And if you'd like to, pause and do it on your own. I will now work it out. Okay. So what's the derivative of the first component? Okay. So just look at this 3 times e to the power of negative 4t. Differentiating, we get negative 12 e to the negative 4t. How about ln of 1 plus 2t? Okay, let's see, differentiating, get 1 over 1 plus 2t times 2, which becomes this. All right, third component. Now, this is where knowing the rules of differentiation can help us. This is product rule, right? So be careful. This would be 2 times sine of t plus 2t cosine t. Running our room. And I'm done. That's r prime of t. Now, here's an example that is important to be able to do. You might see this in the homework or in the textbook if you're working problems. How did we jazz up the problems when we were talking about derivatives of a single valued function, right? I had f, And at the most basic, I might see a problem that just asks me to calculate f prime, right? But maybe the question is phrased, find equation of line tangent to f at a certain point. Okay. Now, remember how we solved these questions. Finding the derivative was part of it, but then, all right, we had the derivative and we maybe had a point on the line, and we had to combine that information to find the equation of a line, a tangent line. Okay. So that's what's going on here. We're asked to find a tangent line, and finding the derivative of that vector valued function is only going to be part of the problem. Okay, and there's a couple ways we could solve this problem. We could be told to find the equation of the tangent line when t equals 0, or we might be given a point, 2, 4, 1. Okay. So let's solve part A first. Okay. Finding the derivative is going to be part of it. So let's go ahead and find r prime of t. Well, what is this? I differentiate the components. So derivative of the first component, 2t. Derivative of the second component would be what? 2t to the negative 1/2. Third component, 2t e to the t squared minus 1. Okay, so that's r prime. Okay. Now, we want to find the equation of the tangent line when t equals 0, so I should probably figure out what r prime of 0 is, right? R prime of 0 is going to be the tangent line at t equals 0. Okay. So r prime of 0 would be 2 times 0, 0. And actually, let's see, I picked a number at random. It looks like t equals 0 is not a good value to pick. Let's pick t equals 3. Okay, so r prime of 3 would be 6. 6 times 2 over square root of 3 times 6e to the 8. Okay. So that's my tangent vector at t equals 3. Okay. But again, this is still just part of the problem. I want to find the equation of the tangent line at t equals 3. So what do I need? Okay, I need something that looks like this. This is the equation of a line, right? The vector equation of a line. So let's see, what have I just found? I have found my line, my vector parallel to our line. Okay. So I know this. And t is just going to be my variable. So what I need, and then r of t is just my left-hand side. So what I'm missing is this r sub 0. So what is that? That is a vector whose endpoint is on the line. I could think of that as a point on the line as well. So I need a point on this tangent line. Well, think about this. Let's say our curve looks like this in 3D space. It doesn't have to be a great drawing. So this is my r of t, and maybe r of 3 is right here. I've calculated the tangent vector. Okay, or yeah, I've calculated the tangent vector, which is a line vector parallel to my tangent line. I need a point on this line. Well, I know that this point, which is on the curve, is on that line, right? That tangent line touches this curve at just this point. So r of 3 is on my line. So how do I find r of 3? I'm going to take 3, I'm going to plug it into my original equation. Okay. So what would r of 3 be? That would be, let's see, plugging in 3 for t, we would get 10, 4 square roots of 3, e to the 8. Again, running out of room. And it might be confusing here because I've used r when I should. So our original function was r. Our derivative is r prime. I shouldn't use the same r for this equation of the line. Let's call it b. So my b sub 0, my point on the line, we said was 10, 4 square roots of 3, and e to the 8. So this would be the vector equation of the line, of the tangent line. Now, we solved this problem when they gave us the t-value. They might not give us the t-value. They might give us just a point on the line. So we want to do the same type of thing. We want to find the equation of the tangent line, but let's assume they don't give us the t-value. Let's assume they give us a point on the line. Okay. So this is it has the same steps. You know, I have my r. What was my r? Let's do some copy and paste here. Okay, so that was my r. And then we went ahead and found our r prime, right? And the general form of our r prime was this. And now we want to find the equation of the tangent line at this point in 3D space, 2, 4, 1. Well, I want the same type of equation. I want b of t equals b of o plus t times v, where v is that parallel vector. Okay. Well, first of all, let's see. This time we're given BO. We're given 2, 4, 1. Okay. Now we got to find V. We got to find explicit values of V. Okay. So at 2, 4, 1, what are the components of my tangent vector? Well, to find that, I have to find the t value that corresponds to this point. What I mean is, okay, again, we have this curve in 3D space, right? And I have this curve, and this is a function of t, right? This is r of t. So maybe at t equals 1, I'm here, t equals 0, I'm here, okay? And then I'm told, okay, 2, 4, 1, let's just say for the sake of argument, this is 2, 4, 1. I'm told 2, 4, 1 is on my curve, okay? I need to find the t value that goes along with this point. So what t value is that? So to figure that out, what I'm going to do is I'm going to look at r of t, my original function. Okay. So for what value of t am I going to get the point 2, 4, 1? Okay. Well, let's look at the first equation. Okay. What value of t for the equation t squared plus 1, what value of t is going to give me 2? Well, t equals 1 would work. Okay, so t equals 1 is a possibility. but I need to double check and make sure that works for my other two components as well. So if I plug 1 into the second component, I get 4 times square root of 1, which is 4. Okay, so I'm getting the point. 2, 4. Let's check our third component. I plug 1 into there. I get e to the 0, which is 1. All right, perfect. So it looks like this point is at the value t equals 1. So now I'm going to take that 1 and I'm going to plug it into my derivative. Okay. When I plug t equals 1 into my derivative, I get 2 times 1, so 2 over the square root of 1, which is again 2, and then I get 2 times 1 times e to the 0, which is 2. So I get 241 plus t times 222. And that is the equation of my tangent line. Now, we have two different tangent lines, right? So these are two different tangent lines at two different points on our graph. That's why we have two different equations here. Now, just a quick note about tangent lines, tangent vectors. These tangent vectors, so for example, we found two different tangent vectors for this problem we did here, right? And one of them, the tangent was this, 6, 2 over square root of 3, 6 times e to the 8. And the other one, it was this. It was nice and simple, right? 2, 2, 2. Now, maybe it's obvious that these tangent vectors have different lengths, right? Maybe one is what it would be square root of 12 units long. This one would be square root of 12 units long, and this looks longer than that. So these tangent vectors have different lengths, and how do we interpret those lengths of those tangent vectors? Well, let's not worry about what the length of a tangent vector means. Maybe we take the derivative of our vector valued function when we get like a tangent vector for 100,007. Okay. What is the length of that tangent vector? Does that give us any kind of qualitative information compared to a tangent vector that looks like this? Okay. Well, let's not think about that too deeply right now. Okay. Really, these tangent vectors are just about direction. That's all we're concerned with right now. These numbers just kind of give us an idea of what direction that tangent is pointing. And so these lengths of these tangent vectors maybe gives us these false impressions that, okay, one tangent vector is more important than another or something like that, and that's just not the case. So to kind of do away with this idea, maybe it would be helpful if all tangent vectors had the same length. Maybe it would be nice if all tangent vectors had length 1. Okay, so this idea has a name, and we call it the unit tangent vector. So what does unit tangent vector mean? It means the tangent vector with the unit length, unit being 1, right? So we often want to compute the tangent vector with length 1. Okay. So going back to this curve, maybe at this point here, I can compute the tangent vector, and it looks like this, and maybe it's got like length 10, etc. And maybe this length of 10 gives us these kind of false impressions about what this tangent means. So let's just take that tangent vector we found and let's kind of modify it and get it to be length 1. Okay. So how do we do that? Well, the first thing we're going to do, so let's say this blue curve is our function s of t. Let's just go ahead and find s prime of t. Okay, so that finding that tangent vector, that first idea of the tangent vector is our first step. So we're going to find s prime of t. And then what we're going to do is we're going to calculate the length of s prime of t. Okay. And then we're going to take our vector and divide it by its own length. Remember from, I believe, section 12.2, this is the idea of a unit vector, right? This, if I take my vector and divide it by its own length, that's going to give me a vector that points in the exact same direction but has length 1. Okay. And that's going to give, so in the case of the tangent vector, that gives me the unit tangent vector. And the unit tangent vector, we use it in a lot of calculations. We give it its own special notation, capital T of T. Okay. Where this T, it's usually a bold T, or we can think of it as T with an arrow over it. That's our notation for our unit tangent vector. So big T for tangent, unit tangent. Okay. So you'll see that notation a lot. So let's find, let's assume our S of T, our vector valued function, is given by this here, sine of T, cosine of T, T cubed. So let's do these 3 problems, and feel free to pause and do them on your own. Let's find S prime of T, let's find the unit tangent vector, capital T of T, and then let's find T of 1. Okay, what's S prime of T? Well, remember, to find S prime of T, I just take the derivative inside the vector using my normal rules of differentiation. So that's my S prime of T. All right. Now, how do I find capital T of T? How do I find that unit tangent vector? So remember our steps. Go back if you need to. So we found our S prime. Right? That's what that was. What was step 2? Finding the length of that vector. And we could do that for a specific T, right? We could like plug 1 in for T and find the exact length when T equals 1. But let's keep it general for now. Let's say I want to find S prime of T when I don't know what exact value T is. How do I do that? So think back to, this was in section 12.3, I believe, when we were talking about dot product. Remember, this magnitude of a vector is the square root of a vector dotted with itself, dot product with itself, right? So using that idea, the magnitude of S prime is going to be cosine squared of T plus sine squared of T plus 9 T to the 4th, right? And then this is what? This is 1. Cosine squared of T plus sine squared of T is 1. Okay. So this is my length of my tangent vector. All right, so that was step 2 in finding my unit tangent vector. So let's put it all together. That means T of T will be 1 over the length times the tangent vector. In other words, this. And we can double check this if you want to double check that this is the unit tangent vector. First of all, it points in the same direction as the tangent vector, right? Since these components are the same as the tangent vector, these vectors are parallel. But I'm dividing this one by a scalar, or I'm multiplying this one by a scalar. So this is a scaled version of my tangent vector. And if I computed the length of this vector, what's the length of this vector? Well, I could use my dot product formula to calculate the length, and it should come out to 1. It might be a difficult calculation, but it should come out to 1. Final step, or final problem, what if we want to find the unit tangent vector at a specific t value? Okay, well, I'll just take that value 1 and plug it in to my equation here. So t of 1 will equal to 1 over, let's see, square root of 10. Cosine of 1, negative sine of 1, 3. Now let's discuss some properties of these derivatives of vector valued functions. They should be pretty familiar because they're almost identical to the derivative properties for functions of a single variable. So first of all, we have these linearity properties, which is just a fancy way of saying, okay, if I have two functions added together and I take the derivative, it's the sum of the derivatives. If I multiply a function by a constant and take the derivative, it's just the constant times the derivative. So those are pretty straightforward. You can look at those for a moment and digest them. The next three are interesting because this is three different versions of the product rule. So remember product rule for a single variable. So let's say I have f and g from R to R. Okay. Remember derivative of f times g is f prime of x, g of x, plus f of x, g prime of x. Okay. Product rule. Here we have three different versions of that for vector valued functions. Okay. Looking at number 3 here, what's going on? I have vector valued function times a normal function from R to R. So maybe it's better to do this. F is from R to R, our usual understanding of a function, and then U is from R to Rn. And again, n is usually 3, but let's just leave it as n for now. Okay, so that's the only thing unusual about this. We have one function from R to R. I plug in a number into this and I get a number out. So this is a scalar. The output of that function f is a scalar. And then I have a vector valued function, so that output's going to be a vector. And then when I take the derivative, okay, it's just the product rule. So f prime of t, u of t, plus f of t, u prime of t. Okay. And what do we have? Let's see, this is going to be a scalar times a vector plus a scalar times a vector. Okay, so the total output of that thing is a vector, right? Because this is just scalar times a vector is a vector. This is a vector, so I'm just adding two vectors together. Next version of the product rule is for dot product. And it still works the same way, okay? Same general way. I'm taking the derivative, and inside this these brackets, I'm taking dot product, okay? So this is a vector dot a vector. So that gives me, what does that give me? That gives me a scalar, right? Okay. Well, it turns out when I take that derivative, I get u prime dot v plus u dot v prime. Okay, so this gives me a scalar plus a scalar. So output is a scalar. And then finally, we have product rule for cross product. Okay, so what do I have in here? I have a vector cross a vector. That gives me a vector. Okay. When I take that derivative of u cross v, it's u prime cross v plus u cross v prime. So 3 versions of the product rule. So it's pretty straightforward. If you ever see anything with these vector valued functions, if it's ddt of anything, where it's something times something in any way. Remember, we have a few ways to multiply with vectors. Okay. So I'll put times here. Okay, blank times blank. It all follows the same pattern. It's u prime blank, or let's call this a and b. It's a prime b plus a b prime. Okay, and then whatever's in here, this times, whether it's dot product, scalar multiplication, cross product, that goes in between a and b as well. So let's say whatever's here is going to be there and there. Okay, so pretty straightforward. You really only have to memorize one kind of this general format. If you know that, you can do all these 3. Last property is the chain rule. Okay. So let's look at what's going on here. We have a vector valued function of a function from R to R. So u is from R to Rn. F is from R to R. So what's going on with u of f of t? I'm taking t and I'm plugging it into f, and I'm getting some number, right? Call it s. And then I evaluate u at s. Okay, so that's what's going on. So when I take the derivative of this whole thing, it's just the chain rule. So derivative of u of f of t, f prime of t times u prime f of t. And let's see. Yeah. This is a product rule example. We got a couple product rule examples. So let's do some product rule examples, and then let's see if we can come up with a chain rule example. So let's do this example first. Let's calculate this derivative. Let's let f equal e to the power of 2t, s be a vector valued function given here. Let's find this derivative. So pause and do it on your own. And let's see if it matches up with mine. Okay, using the product rule, let's see, f prime would be 2e to the 2t times s. This is scalar multiplication here. Then I add what? I add e to the 2t derivative of s prime, which would be 1 over 1 plus t, 2t, negative sine of t. Okay. So I need to add these 2 things together. This should be enough, but we could put it all together as we could factor out e to the 2t, and then I'd have 2 ln 1 plus t plus 1 over 1 plus t, 2t squared plus 2t, 2 cosine t minus sine of t. This is another dot product with, another product rule, this time using the dot product. Okay, so again, pause and do it on your own. Let's see if it matches up with mine. So this is going to be r prime of t dot s of t. So let's see, 2 e to 2t, 1 minus 2t, no, 0 minus 2t, negative 2t, dot s, so dot tan okay, plus r dot s prime. Well, let's see, what's the derivative of tan secant squared, hopefully? Okay, so I need to add these dot products together. And maybe I'll skip that step. Maybe I'll let you guys do that. Well, I guess I should at least take the dot product. Let's see. No, I think this is good enough. If you've gotten this far and your answer agrees with mine, looks like we're on the right track. The rest is just computing the dot product, which looks kind of messy, but it's just straightforward computation. Now let's see if we can link up an example for the chain rule real quick. Okay, so let's say our u of t, let's say that is given by the vector valued function, how about 3t for t cubed sine of t. And then let's say f of t is equal to, how about ln of 1 plus 3t. First of all, you might be asking, okay, what does u of f of t look like? Well, this is just composition of functions. So remember how you do composition of functions. If I have u of f of t, what do? I take t and plug it into f. And then I take that output and I plug it in for t in my function u. So this composition would be what? 3 ln 1 plus 3t 4 ln 1 plus 3t cubed, and then sine of ln 1 plus 3t. Okay, now one way to compute this derivative is just to find this and then take this derivative. Okay, another way to do it is using the chain rule. From the chain rule, I know, okay, if I have u of f of t, that derivative, what is that going to be? It's going to be f prime of t. What is that? Well, f of t is ln of 1 plus 3t. So f prime of t f prime of t is going to be 3 over 1 plus 3t, right? Okay. Now what's u prime? U prime, the derivative of my vector u, well, that should be, u prime is 3 . 12t squared cosine of t, right? That's my u prime. But my formula tells me I want u prime of f of t. So I take my u prime and I plug f of t into it. So plugging f into this, I'll get 3. 12 ln 1 plus 3t squared cosine ln 1 plus 3t. Okay, so that should be my f prime of u, f prime times u prime of f of t. Okay. So that about wraps up differentiation. We have to know all our rules and techniques from Calc 1 and 2 for differentiation. And then we can also talk about integration. So integration, like differentiation, is all about limits, right? Really, calculus itself is almost entirely built on the limit. That's really where calculus comes from. It's this idea of the limit. So we saw that with limits and derivatives, which is just another kind of limit, we can take that limit inside the vector for vector valued functions. Well, it turns out we can do the same thing with integration. Remember, the integral is just a limit as well. But before we get into that, let's first recall integration for a function from R to R. Okay, so before we talk about this idea of integration, you might be coming in with the idea that integration is the area beneath a curve, and we talked about this in our Calc 2 class last semester, for those of you who had me. We could think of integration as giving us the area beneath a curve and so on. And that's, having that intuitive idea is good, but sometimes it gets in the way. So just for a moment, let's kind of forget about that geometric idea of what integration means and just think of it in pure mathematical terms. In pure mathematical terms, the integral is really just the limit of this sum. Okay, so we have a sum that looks like this, and we take the limit as this delta xo, this gap between our x's, this delta x. We take this limit as this gap gets smaller and smaller and smaller. Okay, and that's what the integral is. It's a way of computing an infinite sum. Okay, so that's all an integral is, and that infinite sum has a special form and all that, but really it's just adding up an infinite amount of objects, and it has this structure as we kind of take the limit. So let's just think about it in those terms for a moment. Okay, so what is the integral when I have f from R to R? What is the integral? Let's talk about this limit a bit more in depth. Well, I start with a finite sum. Finite, just look at this, okay? So I have some interval from A to B, and I chop that interval up into pieces, okay? And I have a function, and I take a functional value in each of these intervals, and I multiply it by that width, and I add those values together. Okay. So that's what's going on with this finite sum. And then I take the limit as this gap between values gets smaller and smaller and smaller. And I chop this up into more and more pieces. Okay. So that's what this is. And when I take that limit, the integral just gives me a scalar number. Okay, when I evaluate the integral from a to b, the output is just a number. Now, there's nothing special about this infinite sum here, or this finite sum. Excuse me, it's finite inside the limit. There's nothing special about this finite sum here. We can make the same kind of finite sum for vectors. Okay, and then we know we can take the limit of vector valued functions. So once we have this thing, we can take its limit. Okay, and that's how we define the integral for these vector valued functions. So let's assume we have this vector valued function now. Okay, let's define what the integral from a to b of s of t is. Okay. So again, let's start with this kind of finite sum here. S of ti times delta ti. Okay. Well, what is this? Well, s of t is my vector valued function. I'm evaluating at a finite number of points ti, and I'm multiplying by the distance between those points, delta ti. Okay. So what is this? This is a vector. This is a scalar. So vector times a scalar, that's a vector, right? So this whole thing is a vector. All right, and then I take the limit as this gap between TIs gets smaller and smaller and smaller. Don't worry about it too much. The idea is I'm taking the limit of a vector, right? Well, that means I can take that limit from my previous work in 13.1 and what I've done so far. We've seen that we can take this limit inside the vector. Okay. So this vector, before we take the limit, I could think of the components, each of the components of this vector. Well, the first component would look like this, right? I have these functions f, and I'm adding them up. Same thing with these g's and h's. Okay, and then I'm taking the limit of this thing. And from my previous work, I know I can take the limit inside the vector. Now, what happens when I take the limit inside the vector? If I have limit right here, if I take it inside the vector and I put it here, what is that? Well, that's the limit of the function of a single variable, right? So this is just our normal idea of the integral for a single variable. So this is just f of x dx, which I've written here. And then I do the same thing. I've also taken the limit in here and in here, right? So that becomes integral of g, and that becomes integral of h. Okay. So again, if that explanation doesn't do it for you, just know the idea that if I want to take the limit of a vector valued function, let's say s of t equals f of t, g of t, h of t, and I want to take the integral from a to b of s of t, well, I just take the integral inside the vector and take the integral of each component. And when I'm doing this, again, I need all the integral techniques from Calc 2 that we learned. I might have to do u substitution or partial fractions or something on these integrals, but the only new idea here is that we're taking the limit, or excuse me, we're taking the integral inside the vector. So before we do kind of a practical example, let's just do some computation. So let's say s of t is about 3t cubed ln of t e to the t. what is the integral from 2 to 4 of s of t dt? So pause and do it on your own, and now we can do it together and see if we agree. So I just take the integral inside my vector. So essentially what I have is this. And I can solve each of these three integrals easily. Okay, and that's, each one is going to give me a number, and that number goes in my that slot of my vector. Okay. So what is this first integral? Let's see if we can do this mentally. It'd be t to the 4th over 4, so 3/4 t to the 4 from 4 to 2. So evaluating that, let's see, what's 4 to the 4? Oh, God. Let's see, 1664, 256. 256 minus 16, something like that. So 3/4 times 240. I apologize if my arithmetic's messed up. Okay, what's ln of t? What's the integral of ln of t? Ugh, why did I pick that one? What is it? X ln of t minus ln of t, something like that. This would be a integration by parts, right? You know, I can pretend there's a one, you know, there's a 1 there. Same thing. Ln of t, 1 times ln of t is the same thing as ln of t. And I call this my dv. I call that my u. I do integration by parts. I believe, you can double check me on that. I believe it's t ln of t is minus t. Yeah. And then evaluating from 4 to 2. Let's see, so that would be 4 ln of 4 minus 4 minus 2 ln of 2 minus 2, something like that. And then e to the t, e to the 4th minus e squared. Okay. So that's my integral. That should be my integral. Hopefully you guys got the same thing. Correct me if I made a mistake there. So this is just a purely mathematical, purely numerical thing, right? Now, you might be craving in one of those intuitive ideas like area beneath a curve or something that kind of fits in nicely with this, so you can kind of think about it that way and really understand those terms. But something like that might not really exist all the time. Okay, so we have to think of these mathematical objects not necessarily in terms of geometry all the time, but just in terms of definitions, what they're defined as. So we have to kind of keep the pure definition of this thing in mind. It's the integral of this vector is just the integral of the components. Okay. Now that doesn't mean this is totally devoid of applications. This has a lot of applications. So one application, you know, and this is maybe the best way to understand it, not necessarily in what it means in terms of geometry, but you know, try and think about it as a tool you can use, and all the different situations you can apply that tool to. So let's think about a plane traveling through the air real quick. And we're not going to do a real heavy numerical example, just a quick kind of thought experiment almost. I guess I wrote down some numbers. We could do a numerical example. But let's imagine a plane traveling through the air. Okay, and when we're thinking about a plane, you know, it could be traveling kind of in. Oh, what did I do? It could be traveling in kind of 3 dimensions, right? It could be traveling this north, south, east, west, okay? That's 2 dimensions, and then up and down, all right, that's a 3rd dimension. So let's assume this is the x-axis, right? So let's assume the positive x-axis is south, negative x-axis is north, and this is the y-axis. Well, let's assume negative y is west, positive y is east. And then this is the z-axis. Let's assume positive z is up, negative z is down. So let's assume this plane has velocity, right? Depending on the time. Okay, velocity. If you've done physics, you know what is velocity. It's a pretty much a velocity is a vector, right? It's a magnitude in a direction. So they're using the same idea of a vector in maybe your physics 1 and physics 2 class. So let's say the plane has a velocity given by this vector valued function. Okay, so maybe at time t, it's moving negative 20 units in the x direction, which we've said, okay, that means it's moving at time t equals 1, it's moving, well, at a time t, how about that? At time t, it's moving 20 times t in the north direction. Okay. At time t, the plane is moving 400 t squared in the y direction, positive y direction, which would be like east. And then it's moving 30 t up in the positive z direction. Okay. So maybe my plane has a velocity function that kind of looks like this. Okay, in 3D space, where like, okay, this point is maybe here. And then this point, okay, maybe that's, hopefully that gives some indication of the orientation we're dealing with. So we see it's kind of traveling northeast and it's climbing in altitude, okay? Something like that. That's just a rough sketch. What if I want to know the distance it's traveled in each of these directions after t units of time? Let's say t is minutes. Okay. So let's say I want to be able to figure out how far east it's traveled, how far north it's traveled, and how far up it's traveled after 30 minutes. Well, that would be a great application for this integration. If I do the integral of v of t from 30 to 0, well, I know that's just going to be the vector of these functions, or these integrals. Now, each of these vectors, or each of these integrals I could solve, and they're not particularly hard integrals either, right? And that's going to give me some numbers, and I'm not going to bother finding those numbers. So let's say it gives me numbers a, b, and c. Okay, how do I interpret each of these numbers? Well, a would be the distance traveled north-south, right? And then north/south direction. B is distance east-west. And then C would be distance, vertical distance up-down. And that gives me a vector, right? ABC is a vector. And then maybe if I took the magnitude, the length of A, B, and C, that would tell me the total distance traveled, right? So that's just one application of this integration of vector valued functions. And I think this is the way to think about it, not necessarily in what it means in terms of geometry, right? There's no, this isn't giving me necessarily the area of the stuff under that curve. And maybe that's not necessarily the way to think about it. Maybe it's better to think about what you can use this integral for, and kind of keep the mathematical definition in mind and just think about what that tool can do for you. Okay. All right. So pretty short explanation of integration that kind of matches the length of the definition and the length of the discussion in the textbook. One last thing to say about this was a definite integral, right? We could also do indefinite integrals. So remember, okay, if I don't have bounds here, I get an indefinite integral. Okay. Same rules. I take the integral inside the vector. And just like with integration of a single, integration of a function from R to R, when I have an indefinite integral, I should end up with a constant of integration, right? I end up with the same thing here. But that constant of integration, instead of being just a scalar, it's going to be a vector. Okay? But I could still think of it as a constant of integration. So I would have, you know, the vector of integrals here, and then I could write a plus vector c out to the side to represent that constant of integration. So I think that's the only additional topic they discussed with respect to integration. That is all.